Hello again, everybody. I'm back, and this is going to be kind of a part two to my previous video where I explained my operating systems I've been running in Rust for the past, I guess you could say, 5 months. Although this particular iteration has been only for about a week. So this is going to be unedited. This is going to be just a raw recording of me just kind of rambling about my passion project. This time around, I'm going to try to go into a little bit more detail about how exactly this works um, and talk about some things that if you are new to running operating systems, you may not know about. So, um, first things first, let's get a quick demonstration going. Going to go ahead and run, and it's currently set up to run in a serial console. I'm gonna get this up and running. LLV or LLDB is kind of annoying because it makes me, oh come on. See, I ran into this issue in the other video where I had straight breakpoints and then I did a cargo format and then it just messed everything up. So this is Ash. This is a BusyBox shell. From here we can let's see, if I try to do an ls it probably won't work, but oh, worked first try, what do you know. But now it's not giving me back like the prompt. So something with the scheduler and signals probably is broken. See, if we look at my logs here, it says it says PID equals 1. It's been waiting, but has nothing to wait on because its subprocess PID 5 has already exited. So gotta fix that. Still gotta get to that, but for now, we have a BusyBox prompt. You notice it no longer says anything. No longer complains about not being able to access the TTY. That's because I actually implemented the proper syscalls in order to get it to, be able to access the TTY and be able to do job control. So now it's just frozen, but because it's waiting forever. But we can actually just close this. Then they'll disconnect it automatically. Yeah, there we go. So where I left off last time was I wanted to talk about the task system and the scheduler. But before I do, I had someone ask me some questions about how things like the GDT and the IDT work. So I'm going to go over those real fast, just a little, my thinking process when it came to implementing these. So if you didn't know, in x86 and really any 8086 descended Intel 8086 descended processor, it has this concept called segmentation. And segmentation is a very outdated concept. But if we go to like here, x86 segmentation. So yeah, it's a very outdated process, but basically this kind of let's see, goes over how it works. You can look it up if you're really interested, but essentially how it works is back before processors, but back in like the 80s when you had 8-bit processors, but you had a 16-bit address space. Well, an 8-bit processor can't access 16 bits of memory because its pointer width is 8 bits, So it can't access any pointers that are higher than the maximum value of 8 bits. Or similar concept, if you have a 16-bit processor, then you can't access any memory addresses that are bigger than 16 bits. So how they fixed that was essentially by adding a certain offset to the, sorry, that was my phone again. This is probably going to happen a lot throughout these videos. Freaking spam. All right, it's on my bed again. It's going to become a motif with my videos, I bet. Where was I? Yeah, so the x86 or the 8086, it would add an offset to whatever address was currently being accessed, and that offset was called the segment. And you had different segment registers for different purposes. You had a few, like, you had like a code segment for whatever segment was containing whatever code was being executed. You had a data segment for similar purposes for read and write data, and etc. So eventually, when processor architecture caught up to memory pointer widths, the segment registers ended up becoming obsolete, and so excuse me. But for some reason, for whatever reason, even in modern x86 64 processors like the Intel Core i7 and all that, and even in AMD processors, because they had to make them compatible, right? So with their competition, you need to still load these segment registers with the correct values, or else your computer will not boot. So it's just a side effect of going with such a powerful, complex instruction set processor like the Intel or the AMD or just the x86 or x86-64 in general. So basically, but what the GDT is it basically tells the processor what segments are being used and how. So the GDT stands for Global Descriptor Table, and basically you load this with certain values, with certain flags, in order to tell the processor how each segment selector is being used. It's a little weird. It's a little complicated. Took me a while to figure this out. But fortunately, there's a very fantastic crate in the Rust ecosystem called x86-64 that has these structures in it that just allow me to have all these structures and not mess them up, basically. So, or not mess up their structure at least. And then the actual loading of all that is done via assembly instructions that are inside this crate. So, but for example, when I initialize the GDT, I also initialize the TSS, the task state segment, as you can see right here. That is a special segment located in the TR register that contains things like stack pointers for different privilege levels. So if you implement a context switch mechanism between user mode or privilege level 3 and kernel mode or privilege level 4, privilege level 0, so you have ring 3 and ring 0, right? This is where the concept of rings comes in. It's just different privilege levels depending on what instructions can be executed at any given point. So if you have a context switch mechanism for multiple, processes or tasks in an operating system, then on every context switch, you're gonna have to save its, stack pointer, the stack frame to the TSS, in order for it to, or more accurately, you're gonna have to save its stack pointer in, its kernel stack pointer. It's a whole deal, but every task has a kernel stack for use for when the task is active, but it needs to jump into the kernel for whatever reason, like for a syscall or for an interrupt. So that gives the kernel a little space to work with inside that task that's exclusive to that task. So it's a task local, thread local structure. I mean, it's all in the name, right? Task state segment. It's a segment describing the state of the current task, right? So, so you save the kernel stack pointer for that task in the task segment, and if you want to switch tasks back to a different task, then you need to save it in that task segment. And then if you want to be able to keep track of the kernel's information throughout all this, then you're going to need an extra structure. And that's why I have in CPU local.rs here, I have this kpcr kernel processor control region, I think it stands for, or something like that. Or kernel per CPU, I don't know, record. I got this name from somewhere else, but this is where I have the kernel SP, and then I have the TSS for each CPU, each task, each core. Assuming each core runs on, each task runs on its own core, which it currently doesn't, but same concept still applies, right? So, yeah, so in here, we basically just initialize memory for the kpcr and for the TSS. We alloc some, yeah, so this is, sorry, let me back up a bit. This is going to, this init boot is before we have the heap set up, and this init, that's actual init, is after we have the heap set up. That's why we're able to use alloc to allocate some zeroed out memory in the layout of a kpcr or of a TSS and all that, So we basically allocate some zeroed out memory for that. We then get our pointer into it and set it up to be an initialized task state segment. We set the privilege stack table for ring 0 to be the kernel's own stack. This is just until we jump into user mode or switch tasks. This will be saved in the kernel RSP of the kpcr in order to so we can switch back into the kernel during a syscall, for example. So, and then we initialize our GDT. Just flags that go into all this, like kernel code segment, kernel code 64. So see, if you go into this crate, it's got all the descriptor flags. So it's got all the column flags, and then it's executable code, and it's for long mode and protected mode and all that is its own kind of worms, but it's basically whether processors are operating in 16-bit, 32-bit, or 64-bit long mode, right? So 16-bit would be I actually don't know what 16-bit mode is called, but 32-bit is called protected mode, where the processor can only address, at least I think that's how it works. It's like it can only address like 30 bits. And then in order to get to long mode, you just set the appropriate flags in the control registers, and then perform a long jump. And you have to do that in assembly code. Now, fortunately for me, Lamine does all that for me. Sets me up with long mode, sets me up with the GDT even, and I'm replacing it with this one that I create here. So yeah, we just set separate segment selectors to just tell us what segments are going to be used for and how they're going to be used. And we load our registers, our segment registers, CS, DS, ES, and SS, with the appropriate selectors, appropriate configurations, and we load our TR register, load TSS, with our TSS, or at least our initial TSS, the one that the kernel has. So, and then IDT, to quickly go over that, even though I said I'd quickly go over the GDT, and it's been like 10 minutes. But the IDT is for interrupts. It's a similar concept to the GDT, except instead of segmentation and various privilege levels for different, modes of operation for the processor. This is all dedicated to interrupts. So if you didn't know, when any hardware event happens, you get something called an interrupt that's fired by the hardware device, and it's picked up by the processor. And it as it says in the name, it interrupts the processor's chain of execution or flow of execution, and the processor has to do something with the interrupt, or it can just choose to ignore it. But either way, if you don't have a handler for an interrupt, then if the interrupt isn't masked, then you'll get what's called a double fault, and if you don't have a double fault handler set up, then you get what's called triple fault, and your computer will reboot automatically. So, and it's entirely possible to get boot loops where your computer just reboots over and over again if you keep triple faulting with a bad interrupt table or bad interrupt handlers. So, yeah. So there are certain interrupts that are special. They're called CPU exceptions. They can happen at any point, basically, and they need to be handled, or else, like I said, that double fault will happen. And double fault is also a CPU exception. So if that doesn't have a handler, then yeah, you're boned. You triple fault, computer reboots automatically without you being able to control that. So, so there's a bunch of these interrupts, 32 of them, in fact, or exceptions, I should say. There's 32 of them. Yeah, there's 30 actually. There are 30 interrupts, but sorry, 30. What am I saying? 30 exceptions that need to be handled. Although some of those do include some reserved parts of the IDT. Why they're reserved, who knows? But that's just how Intel made it. So, and then we have the IDT is actually, I believe, 256 long. 256 entries long, so it can hold 256 bytes of information, unsigned 8-bit integers. I guess if you could call it a U8 in Rust. So it can hold 256 of these things. So you have 226 226 vectors in this IDT that you can use for your own interrupts. And so this would be things like hardware interrupts, like the system timer or the serial port, and you can set these up by using the appropriate, I/O instructions for whatever hardware you're using. In my operating system kernel right now, I'm currently emulating a system timer in the form of a PIT, programmable interval timer. And I'm setting and I'm emulating 2 serial ports. One is for the log, and one is for interfacing with the user. So this one right here. So with the interrupts, whenever an interrupt is triggered, the CPU saves the state of most registers at the time that the interrupt happened. And you can see all these registers right here. These are the preserved registers. These can be, I believe these need to not change during the course of the interrupt handler, or at least they need to, be the same on entering the interrupt and on exiting the interrupt. These are what we call scratch registers. I don't really know what the difference is. I'm pretty sure these need to be the same as well, or at least it's, the CPU will be happy if they're the same. And then these are what we call the IRET registers. And IRET is an instruction that is used to return from an interrupt. So these can be used to control where the CPU jumps to and what kind of privilege levels it jumps to, what flags it uses, and what stack pointer it uses upon returning from that interrupt. So you can use this for some cool things, such as jumping to user mode, with an IRET. Jumping to ring 3, by setting the CS and SS registers in the stack frame to the appropriate values. So just that's actually how we end up jumping to user mode. How you used to end up jumping to user mode. There's another way to do it by using a syscall return instruction called sysretq or sysret, and I'll talk about that in a bit. But and then like I said, this is the assembly code to handle interrupts. I have a calling function called x64 handle interrupt that is down here. That just does a big switch or match statement if you're a restation like me. Switch if you're a C programmer. I don't know what you call C programmers. But essentially what it does is it just tests it checks if we enter the interrupt from user mode. If so, we swap our GS register, we swap our GS base register, which is used to store the CPU local information and the task specific information, like the TSS, like I talked about before. The GS base is an offset, just like, because segmentation, it's all coming together, right? So we swap our GS register, or swap our GS base register so the base of the GS register points to the correct CPU local information. So we set up our interrupt handler to be able to access the stack at the point at which the interrupt happened. After the interrupt has been handled, first of all we pop the error code by adding 8 to the stack pointer. Pop the rest of the registers off the stack, and again, if we were in user mode before, then we switch back to the users TSS and all that, and then we return from the interrupt with IRET, like I said. So, and this is all just boilerplate code to get all that working. So, yeah. So really, I'm kind of out of time. I could go on to talk about the task system and all that, but I had someone ask me about how all this works, so I explained it. So I'll do another follow-up to this video where I actually go over the task system. It's something I'm working on a lot right now anyway, so it's very much subject to change even from day to day. So yeah. Anyway, thank you all for watching, and we'll see you next time. Peace out.